Hello everyone, welcome to the second part of this series on a sensorized garden. In this part, we will talk about the bill of materials used to build the system. We will then briefly discuss the hardware design choices before moving on to the software design choices. We will not talk too much about the hardware design as we are mostly buying parts off the shelf and not designing them ourselves. Each of the sensor and actuator components could be an interesting topic on its own. On the hardware bill of materials, I realize I have an international audience here. Currently, I live in the United States, and it is relatively easy and cost-effective to source these components. When I was an engineer in Nepal, it wasn't easy to source these components. If anyone in the audience wants to build this or similar systems and has difficulty sourcing the parts, I would be happy to discuss and assist. Also, please feel free to comment on the video or the GitHub site on availability and alternatives. First, the Raspberry Pi. For this project, it is likely that a lower cost version like a Pi Zero will also work. However, if you are not budget constrained, I would encourage you to get the Pi Model 4B here, as it is much easier to set up and run the Python software and library modules. It's easier to load the Ubuntu operating system with a higher end computer. If you manage to get it working with a lower end Raspberry Pi, leave some comments and we'll also document it in the GitHub repository. The resistive soil moisture sensor here, the resistive soil moisture sensor measures the moisture near the plant roots. As the name implies, I specified one that is corrosion resistant. The air temperature and humidity are again important factors for keeping healthy plants. Different plants require different temperature and humidity levels, and different plants require different light levels. There are many excellent resources for general advice for different types of plants. However, there's probably not a database for detailed minute by minute data on how plants do well or not, except for a very limited number of plants. Once we collect data like this, then we will have more opportunity to create such a database. The $30 kit is probably all you need to get started. It has moisture sensors and water pumps, but I decided to add a few more to collect higher fidelity data such as temperature, humidity, and also use a different corrosion resistant sensor. Additional tools that could be helpful for troubleshooting include an oscilloscope, multimeter, and basic tools like screwdrivers and soldering irons. Relatively low cost ones will do for this project, as we are not using the tools to develop the electronics, but just for basic troubleshooting. Of course, you will also need a computer, a screen that is separate from the computer with HDMI input and keyboard. A mouse will also be helpful to set up the Raspberry Pi. I did have an interesting incident where I traveled to a different city to work with a friend for a day, and we spent half a day just finding a screen with HDMI input and matching cable. Stuff happens. The lesson is list these things down even if it seems excessively detailed. Often the trick in doing good engineering work is attention to detail. Now, moving on to the software side. These are the software components that we will be using. The Ubuntu operating system for the server, GPIO 0 for the server, Python 3.9 for the server and the client, gRPC as mentioned in the title of this talk, and it's used in the server and the client as well, PySide, which is a Qt or Qt framework for Python. It's also used for the client. I mentioned these in passing here as we will be discussing them in more detail in coming sections. All of these have alternatives. For example, if we were to develop a web or mobile application client, we could use some frameworks such as Flutter, Angular, or even native frameworks like Swift and Android Java. The important thing to note here is that as designers of a system, we need to understand certain details at a given level of abstraction, while we can take lower level concepts for granted. Over time, as better programming languages and concepts have been developed, we do not need to understand exactly, for example, how memory is being allocated in the operating system. However, at the same time, we now have rapidly progressing mobile device platforms and cloud technologies that we need to understand to be able to build robust distributed systems like this. The more we understand, the better we are able to make intelligent design choices. In many actual engineered systems, a single person may not be able to know every detail, and it is more efficient to work in teams. At the same time, it takes time to understand systems and the environments that they need to operate in, even for teams. So the trade-off is about taking the right amount of time to understand why we take a certain approach. For hobby or do-it-yourself projects, it is fine to follow a tutorial like this, almost as a recipe. We'll now move on to part 3, where we will describe at a high level the system architecture and why we chose some of the options that we did. Thank you.